Alright, so remember that this patch was pretty simple, just looping a certain amount of notes over and over again. Always starting from the same note, which is the MIDI value 64, this E note. So what I want to try to achieve is to start on a random note every single time that the counter reaches its limit or reaches the note 78. And if I just hover over the outputs of the counter, I can see what type of data, what type of output each of these outputs sends out. So the first output which we've been using is just the current count, counter hit minimum flag. This next one is counter hit maximum flag, which is what I want because I want to know when counter hits this note 78. When does it hit the last note? And let's give this output an integer box just to be able to see what type of output we receive once we reach our maximum limit. You can see that every time we reach the last note, which is note 78, this output just sends out a number of 1, otherwise it's 0. I still don't know how this output can help me, but I know that somehow I need to convert the type of information I'm getting from here to be able to activate a random object, right? Because I want to generate a random starting point again for my counter. How do I choose what random numbers I want? Our current counter will start every time on 64. I probably want to go up to 63. I want to have every other number below that note. So remember, random starts from 0. So if I actually want random numbers up to 63, I still need to type in random 64. That way I'll get 0 to 63. However, I really don't want to go too low in a sense that it will be inaudible to us. Let's see like what's the lowest number that I want to go. I would say probably somewhere around 47. Now, remember, I can't just give random a range. I can't say random 47 to 64. Random will always start from 0. But what I can use is I can use this object called split. What split does is that it only lets a certain range of numbers to come out of it. So let me just demonstrate that individually. If I say split 1 through 10, so we can give it 2 arguments. The first argument would be your minimum, the second argument would be your maximum. And let's give an integer box to its input and 1 to its output. So what split does is that it only lets numbers from 1 to 10 to come out of its output. If it's a number other than 1 through 10, it's not going to output that number. You can see if it's 6, it outputs 6, but if I go to 17, it's not going to output it. If I type in 10, it's going to give me 10. So this is one way to narrow down the results that a random object will give you. So let's create a split object, and like I said, maybe the lowest note I want to actually play is 47, and I want to go up to 63. So now if I connect the output of random 64 to the input of the split object, even though random will generate random numbers from 0 to 63, 46 won't pass through. Anything lower than 47 won't pass through. And that helps me narrow down the range of the random numbers that I want to get. Cool, so we figured out this part of the puzzle. But once I receive that number, where do I want to go? But first of all, how do I activate random 64 once I hit my maximum? Well, we know that we need a bank to activate random object, right? And this output gives us a 1 once we reach the maximum. So what I really need is a select object, and I want to select a number 1. So the output of select 1 says bang if input matches 1. So I know that it's not going to send a bang when this integer box shows a 0, but it will send a bang once we reach 1, which is indicating we're hitting 78, we're hitting the max. Once we get a bang, I want to connect that to our random object. So now we'll be able to create a number between 47 and 63, a random number between that range, whenever we hit the maximum of our counter. And let's just double check every step that we do. And remember that this is a random object, so you saw that I got the number 50 3 times in a row, and that's totally okay, because it's supposed to be random, right? Okay, so where do we want to send this number? Let's look at some of the inputs of the counter. What I want to do is to be able to reset this 64 with this random number that I will receive here. So let's just read the inputs of counter. Sets direction, right? If you want to count up, count down, or do a pendulum motion. This one resets the counter to number on the clock. This one resets counter to number immediately. And this is what I want. I want the counter number to be reset immediately after we get this number. What I really need is that the output of my split, and remember, these number boxes are just helpful to us to visualize or what type of process we're making. They're not really essential to make this patch work. It's just a way for us to monitor the changes that we're making. So then let's connect the output of the split or this integer box, it doesn't matter, to that input on the counter, which resets it to that number immediately. Awesome, so it works. It resets the initial value that the counter counts from to a random value between 47 and 63. So far we've been working with the cycle object, which is a sine wave generator. But the starting point for subtractive synthesis most of the times is a square wave or a sawtooth wave, because they're the richest sounding of the waveforms. So you start with a waveform and then you sculpt it, meaning that you take things away from it, you add filters or envelopes to it. So that's how subtractive synthesis works, and that's why you need the richest forms of waveforms, so you can actually take things away from it. Sine wave is really pure, so there's not much to take away from it. Sine waves are the foundation of additive synthesis, which means that you add multiple sine waves on top of each other to create more complex waveforms. Well, let's just change the name from cycle to saw, and just hear how this sounds like now. Listen to the change in the sonic qualities between these two waveforms. So yeah, it sounds pretty harsh, and one way that we can fix that is by adding a low-pass filter. Low-pass filter, otherwise known as high-cut filter, is cutting those higher frequencies out of a sound, essentially only passing through the lower frequency sounds. Pretty simple low-pass filter to use in Max is called onepole. So I'm going to add the signal after the multiplication through onepole, and then just connect the output of that to the both channels of my EZDAC. The first inlet is where you want to pass through your signal, and the second inlet is where you define what the cutoff frequency of this filter is. The cutoff frequency is the frequency that your filter is activating. So if your filter is a low pass filter, the cutoff frequency is the highest frequency that you're essentially passing through, and anything above that frequency will start to roll off or be cut out of the sound. So with onepole, you want to feed in the cutoff frequency to its right inlet. So we can just create an integer box for that. And now let's play around with the cutoff frequency while the sequence is being played in order to fully understand how that cutoff frequency affects your sound. So right now we can't hear anything at all because the cutoff frequency is 0, and the range of frequencies that humans can hear is between 20 to 20,000 hertz. So 20 hertz is essentially the lowest sound that most of us can hear. So of course, if we're cutting anything above 0 hertz, then that's essentially silence to us. So I'm going to slowly start to increase my cutoff frequency, and we'll probably be able to hear that sound eventually. And you can see as I increased my cutoff frequency, the sound became brighter and harsher. I want to still have the richness of a sawtooth, but without those super high frequencies. So I set my cutoff frequency to something around here. One of the other low pass filters that you can use is called low res. And let's open up its help. So it's a resonant low pass filter. Its first argument is the cutoff frequency, and then the next argument is a resonance value, which is somewhere between 0 to 1, or you cannot have it at all. You can see here that you can use the line object even for something like a filter's cutoff frequency to be able to sweep through the cutoff frequency essentially. So 200 hertz is your initial value, and you're going to go to 2000 hertz during half a second, and then you're going to go back to 200 hertz during the span of 1 second. So you can use the line tilde for any signal envelope that you want to use. Alright, so I wanted to show you this patch that is available to download. It has these comment boxes, which, by the way, you can create by hitting C on your keyboard. And this is just a comment, meaning it's just a string of text that doesn't really do anything. It's just a comment box for you or your future users to be able to know what each different section of your patch is doing. And also, a lot of times you might have a genius idea you coded. The day after you open up your patcher and you don't know what you did, or you don't know why you did a certain thing. So just using comments even for yourself is such a good idea to be able to later on remind yourself why you did a certain thing the way that you did. So yeah, this patch just has some comment boxes to make it easier for you to look at it. So this is the section of the patch that we created together. However, you might notice a few differences. The first thing that you might notice is this graphical object, which is the function object. Now, this function object is essentially replacing that message box that we sent to line. So I think the function object is more intuitive because it's visual, and you can manually move these points and line segments around, of course, when your patch is locked. It gives you a better representation of the way your sound will flow. And using the set domain message, you can tell the function object what the length of it is. So if I type in 1000 milliseconds, it means my sound's volume will follow this shape over the span of a second. But if I make it 10 seconds, so 10,000 milliseconds, that means it will follow the same shape but over a longer period of time. And you can also just create a number tilde object, which lets you monitor signals. So if I come from the output of the line, this, and let's hit this bang, I can actually see how my sound is changing over time. So this is how you create a function object. Just type in function. I'm going to be left with just a blank screen. Of course, you want to lock your patch first, and then you'll be able to create points by clicking. And if you want to delete a certain point, you want to shift click on that point. Yeah, and you can move the points around, Again, always same with the messages you were sending to line. You probably want it to end at a 0, otherwise your sound will go on forever. So just make sure you add a last point that ends on 0. And also notice that with this function, I didn't come out of the first output. I came out of the second output because the second output says all points in the line format. And this is exactly what we want because we want to use a line object to be able to create this ramp. So play with the shape of your envelope. Add points, delete points, see what you can do. Let's hear how this will sound like over the span of a second. Or we can increase that to a span of 3 seconds. You can hear that each of these line segments will feel longer. Change it to half a second. Sounds like you're playing it twice. So let's play that around with the metro, but I probably want to make sure my metro is at least 500 milliseconds as well, so the same as my duration. If it's playing faster than that, then I wouldn't be able to hear the full span of my envelope. It will be cut short, and that's okay. But if you want to be able to hear the whole envelope, you want your notes to play at least as slow as your envelope duration. So let's see what else is different in this patch. So you can see that I have two oscillators. So I have a cycle or sine wave oscillator here, and then I have a sawtooth oscillator here. And I'm sending both of those to a multiplication tilde object, and I'm multiplying them by 0.5 because I don't want both of these signals to be playing at full volume. Therefore, if you have maybe more oscillators, let's say if you have 5 oscillators, you probably want to multiply them by 0.2. So after we multiply those two signals together, we're going into a low pass filter called onepole, and out of the onepole to the easy DAC so we can hear it. But also I'm sending the output of the onepole to the sfrecord object, and I'm recording both channels left and right. So the way you use the sfrecord object is that first you want to send a message of open to it, and then while your patch is locked, click on that open message and choose a location on your computer that you want to save it to, give it a name, and then hit save. I know it's kind of counterintuitive because you need to save the file first, and then you can use the toggle to start recording whatever you want to record. And then once you're done with recording, you can hit the toggle again, and then you can access your file that you recorded. So having multiple oscillators in a patch really gives you a lot of possibilities with sound design. First, you can just mesh or layer a bunch of oscillators on top of each other to create richer sounds, but also you can have them play different parts of a song or create different textures with each set of those oscillators. So here, one fun thing that you can do is you can have different metronome settings on both of these oscillators, so they're playing at different tempos, which that could create some cool effects. You can also mess around with their amplitude envelope. And yeah, you can see that the other difference between my saw and cycle oscillator is that I'm using that random starting point for the counter for my cycle, but this other one to the left is going to play the same thing every single time. So let's just play around a little bit.